Welcome, everyone. I'm excited to kick off our presentation today. The title of our talk is Current, Resistance, and Voltage, and we'll be exploring some fundamental concepts of electricity. We'll cover what current is, how resistance affects electrical flow, and the role of voltage in driving that flow. So, let's get started and dive into these essential topics together. Have you ever wondered how your phone charges when you plug it into a socket? It's a pretty common question, but understanding what actually happens inside your device can be quite fascinating. When you connect your phone to a power source, electrical energy flows through the cable and into your phone. But that energy isn't just going straight into your battery. There's a whole process involved. The charger converts the high-voltage AC power from the outlet into a lower-voltage DC current that your phone can safely use. This conversion is crucial because it ensures your phone charges efficiently and safely. This process highlights the importance of power management and the technology behind chargers, which is a key part of the overall theme of understanding how electronic devices operate seamlessly in our daily lives. Let's talk about electric current. This flow of electrons is what we call electric current. Essentially, it's the movement of these tiny particles through a wire. Now, the voltage, or what we can think of as electrical pressure, is what pushes these electrons along. When you plug in a charger, for example, negatively charged particles called electrons that are already inside the wires start moving in the same direction. This movement is what powers our devices. So, in simple terms, electric current is all about electrons moving through wires, driven by voltage. Let's talk about electric current and the role of resistance. When electric current flows through a wire, this resistance causes the wire, and any devices connected to it, like your phone charger, to heat up. Now, what's happening at a microscopic level? Free electrons are moving along a zigzag path, colliding with each other and with the fixed atoms inside the material. These collisions create resistance, which is what makes the wire resist the flow of current. Think of it as a kind of friction within the material that slows down the electrons. This concept of resistance is fundamental because it explains why wires heat up and also influences how electrical devices are designed for efficiency. So, understanding how electrons move and encounter resistance helps us grasp the overall behavior of electrical circuits. Today, we'll explore how to use Ohm's law to find the current, voltage, or resistance in a circuit. This law is fundamental because it helps us understand the relationship between these three variables. When we talk about Ohm's law, we're essentially saying that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. So, if you know two of these values, you can easily calculate the third. For example, if you want to find the current, you just divide the voltage by the resistance. This relationship is key to troubleshooting circuits and designing electrical systems. Now, let's connect this to the concept of current and charge. Current is the flow of electric charge, so understanding how charge moves in response to voltage and resistance helps us see why current behaves the way it does in different situations. By the end of this session, you'll be able to define what current, voltage, and resistance are, and understand how they all work together according to Ohm's law to shape the behavior of electrical circuits. Let's take a closer look at the ammeter and its role in measuring current. As we discussed earlier, current is the rate at which charge flows through a circuit, and this charge is carried by electrons. To understand how much charge is moving at any given time, we use an instrument called an ammeter. The key thing to remember is that an ammeter is always connected in series with the circuit. This means it's placed right along the path of the current flow, so it can accurately measure the flow of electrons passing through. When you see a circuit with a bulb and a battery, and you want to measure the current flowing to the bulb, you connect the ammeter in series with the bulb and battery. This setup ensures you're measuring the current as it flows through the entire circuit, giving you a clear picture of the current's magnitude in amps or amperes. Let's take a closer look at the relationship between time, charge, and current. On this slide, you'll see the key variables: time, which we measure in seconds, charge, measured in coulombs, and current, which is in amperes. The main idea here is that electric current is essentially the amount of charge passing through a component per second. Think of it as how much charge flows through a wire in a given amount of time. The faster the charge flows, the higher the current. The core equation linking these concepts helps us understand and calculate current based on the charge and time involved. Remember, understanding this relationship is fundamental because it underpins many other concepts in electronics and circuit analysis. It's all about how charge moves and how quickly it moves through components, which is what current really measures. All right, let's take a look at this example. On this slide, we're working with three main variables: time, charge, and current. The goal here is to calculate the current flowing through the air conditioning unit. We know that the charge, Q, is 18,400 coulombs, and the time, T, is 1 hour, which is equivalent to 3,600 seconds. But the current, I, is what we're trying to find. Now, before jumping into the calculations, it's important to ask ourselves two key questions. First, what are the given values? And second, which values are missing? In this case, we have the charge and the time given, and we're missing the current. This sets us up for the next step, which is deciding on the correct formula to use. Since we're dealing with charge, time, and current, the fundamental relationship here is that current equals charge divided by time. So, in this example, we're going to apply that formula to find the current. Think of it as measuring how much charge flows through the unit per second. It's a practical way to understand how much electrical flow is happening in the system over that period. This example really highlights the importance of identifying what we know and what we need to find before doing any calculations. It also shows how basic formulas can help us solve real-world problems efficiently. Now, let's look at how we calculate the current in this air conditioning unit. We know that it has a charge of 18,400 coulombs flowing through it every hour. To find the current, we use the basic formula. Current equals charge divided by time. Here, the total charge is 18,400 coulombs, and the time is 3,600 seconds, since there are 3,600 seconds in an hour. When we divide 18,400 coulombs by 3,600 seconds, we get approximately 5.1 amperes. This means that, on average, about 5.1 coulombs of charge flow through the unit each second. This example really illustrates how understanding charge and time helps us determine the current in real-world devices like air conditioners. So, in this slide, we're looking at a circuit where a current of 4.8 amperes is flowing. Now, the key here is understanding what this current represents, essentially, how much charge is moving through the circuit each second. Since we're given the current value and the duration of 45 seconds, we can figure out the total charge that passes through the circuit during that time. Remember, current is the rate of flow of electric charge, so to find the total charge, we multiply the current by the time the current flows. This is a great way to connect the concept of current to real-world scenarios, like how much charge is transferred in a given period. It's a fundamental idea that links the flow of electrons to the overall behavior of electrical circuits, and understanding it helps us grasp how devices operate over time. Now, let's see how we can apply this to find the actual amount of charge that passes through in these 45 seconds. In this slide, we're looking at how much electric charge passes through a circuit when a certain current flows over a period of time. The key point here is that the charge, which we denote as Q, is calculated by multiplying the current, I, by the time, T. In our example, the current flowing through the circuit is 4.8 amperes, and it flows for 45 seconds. Using the formula Q equals I times T, we multiply 4.8A by 45 seconds, and that gives us a total charge of 216 coulombs. This illustrates a crucial concept, the relationship between current, time, and charge. The greater the current or the longer it flows, the more charge passes through the circuit. Now, for this problem, we're asked to find out how much charge passes through during this period. Since we already know the current and the time, we just need to apply the formula, substitute the values, and solve. Let's walk through the steps briefly. First, identify what values we know and what we're solving for. Next, choose the relevant formula, which is Q equals I times T. Then, substitute the known values, 4, 8 amperes and 45 seconds, and multiply to find the total charge passing through the circuit, which is 216 coulombs. So the main takeaway here is that a current of 4.8 amperes flowing for 45 seconds results in a total charge of 216 coulombs passing through the circuit. This example helps us understand how current and time directly influence the amount of electric charge transferred. Let's talk about voltage, which is measured in volts, or V. Think of voltage as the pressure or push that drives the flow of current through a circuit. You can also think of it as the potential difference between 2 points, which essentially tells us how much energy is available to move electrons. Now, to measure this voltage, we use a device called a voltmeter. When you're measuring voltage in a circuit, you place the voltmeter in parallel with the component you're testing, like a bulb or the battery. This way, the voltmeter can accurately measure the potential difference across that component without disturbing the current flow too much. So, when we look at a circuit with a battery, a bulb, and measuring devices like a voltmeter and ammeter, each plays a vital role. The voltmeter helps us understand the voltage across different parts, which is crucial for diagnosing or understanding how the circuit functions. Remember, understanding voltage and how to measure it is fundamental to working effectively with electrical circuits. It helps us ensure everything is operating safely and efficiently. Now, let's talk about resistance, which is measured in ohms, symbolized by omega. Resistance essentially tells us how much a material opposes the flow of electric current passing through it. Think of it like a pipe. The higher the resistance, the more effort or energy is needed to push the current through the component. This resistance can impact how well an electrical circuit performs overall. For example, if resistance is too high, it can reduce current flow and affect the circuit's efficiency. That's where an ohmmeter comes in handy. It's a device used to measure the amount of resistance in a specific component. When you pass a small current through the component, the ohmmeter tells you how much opposition there is. Understanding resistance helps us design better circuits and troubleshoot issues, making sure everything runs smoothly. All right, let's take a closer look at slide 14. Here, we see the symbols for resistance, voltage, and current. Resistance is measured in ohms, which we write as omega, and it essentially tells us how much a material opposes the flow of current. Voltage, represented by Q here, is the potential difference that drives the current through the conductor. And then we have current, denoted as I, which is the flow of electric charge. Now, the key idea here is Ohm's law. It states that the current flowing through a conductor is directly proportional to the voltage across it, as long as the temperature stays constant. This relationship is fundamental because it helps us understand how changing the voltage affects the current, and vice versa. In simple terms, if you increase the voltage, the current increases proportionally, assuming resistance stays the same. Conversely, if resistance increases, the current decreases for the same voltage. This law is central to designing and analyzing electrical circuits, and it ties into the overall theme of understanding how electrical quantities interact. So, in essence, Ohm's law provides a straightforward way to predict how a circuit will behave when you tweak different parameters, which is crucial for both practical applications and theoretical understanding. All right, now let's look at slide 15, where we focus on calculating voltage using Ohm's law. First, we see the formula. Current I times resistance, omega, equals voltage, V. This is the fundamental relationship we use to find the voltage across a resistor when we know the current flowing through it and its resistance. Next, there's an example to put this into practice. The key question here is, what is the voltage? We are given the resistance, which is 40 ohms, and the current, which is 0.6 amperes. Our goal is to find the voltage or the potential difference across this resistor. So, step 1, identify what values we have and what we need to find. In this case, we know the resistance and current, but the voltage is missing. Step 2, decide which formula to use. Since we're looking for voltage, and we have current and resistance, we'll use V equals I times R. Now, plugging in the numbers. V equals 0.6 A times 40 ohms. Multiplying these gives us the voltage, which is 24 volts. This example really highlights how straightforward Ohm's law is for solving such problems. By knowing just two values, we can easily find the third, which is incredibly useful in many electrical applications. Remember, understanding this relationship is crucial because voltage, current, and resistance are the core parameters in any electrical circuit. Now let's look at how we can determine the voltage across a resistor when we know the current flowing through it. The key formula here is Ohm's law, which states that voltage equals current times resistance. In this example, we have a resistor with a resistance of 40 ohms and a current of 0.6 amperes flowing through it. To find the voltage, we simply multiply these two values together. So we take 0.6 amps, multiply it by 40 ohms, and that gives us 24 volts. This calculation shows us that the voltage across this resistor is 24 volts, which is an important concept because it helps us understand how voltage, current, and resistance are all interconnected. Remember, whenever you know two of these quantities, you can easily find the third using Ohm's law. All right, let's analyze this scenario. We're increasing the current from 0.6 amperes to 2.2 amperes while keeping the voltage constant at 24 volts. The question is, what is the new resistance needed for this higher current? Remember, Ohm's law is our guiding principle here. It states that resistance equals voltage divided by current. So, to find the new resistance, we simply divide the voltage, which stays at 24 volts, by the new current of 2.2 amperes. This highlights an important concept. As current increases at the same voltage, the resistance must decrease. It's a direct application of Ohm's law that helps us understand how circuits respond to different conditions. So, by doing the calculation, 24 volts divided by 2.2 amperes will get the resistance value needed for this new current. And this exercise reinforces the core idea that resistance and current are inversely related when voltage is constant. This is a great example of how adjusting circuit parameters affects overall performance, and it ties back to our ongoing discussion about designing efficient electrical systems. All right, let's look at this slide. We've got a resistance value of 10.9 ohms, a voltage of 24 volts, and a current of 2.2 amperes. The key question here is, what is the new resistance needed if we increase the current from 0.6 amps to 2.2 amps while still maintaining the same voltage of 24 volts? What's important to remember is that resistance, voltage, and current are all related through Ohm's law. The formula we'll use here is resistance equals voltage divided by current. So in step 1, we identify our given values. Voltage is 24 volts, current is 2.2 amps, and the missing value is resistance, which we need to find. In step 2, we decide to use the formula resistance equals voltage divided by current. Then, in steps 3 and 4, we substitute the known values into the formula. Resistance equals 24 volts divided by 2.2 amperes. Finally, we solve, and that gives us the new resistance needed to achieve this higher current while keeping the voltage constant. Remember, adjusting resistance like this affects how much current flows through the circuit, which is crucial for designing safe and efficient electrical systems. Let's wrap up with some key concepts about resistance, voltage, and current. Resistance opposes the flow of current, and we measure it in ohms, symbolized as omega. Think of it as a kind of obstacle or friction that slows down the flow. We can calculate resistance by dividing the voltage by the current, so understanding both these quantities helps us determine resistance. Now, voltage is like the pressure or push behind the current. It's what drives the electrons through the circuit. We measure voltage in volts, or V, using a device called a voltmeter. Sometimes, you'll hear voltage referred to as potential difference, because it measures the energy difference between 2 points in a circuit. Moving on to current, this is the rate at which charge flows through the circuit. Specifically, it's the flow of electrons. We measure current in amperes, or A, using an ammeter. The higher the current, the more electrons are moving through the circuit per second. Bringing it all together, these three concepts are interconnected. Voltage pushes the current, resistance opposes it, and the current is the actual flow of electrons. Understanding this relationship helps us analyze and troubleshoot electrical circuits effectively, which is essential in everything from simple devices to complex systems.